Okay, thank you. So I will say with this lesson, there could be a benefit for in-person and a whiteboard, but I will be kind of switching, pausing the presentation, then switching my camera, and we can kind of go over a few things with drawing them out. And I do apologize for my penmanship going into this. But today we're just going to be talking about home mechanical systems, and it really is kind of like two parts. And if we still have time, then we'll start talking a bit about domestic hot water as well. And then as always, we do take a 5-minute break in the middle. But we're just going to be talking about mechanical systems. And really the idea is to understand all of the ways that we've been heating our homes in New England. And based off of the legacy equipment that's inside of the home, highlight some of the complications with, say, adopting a partial home heat pump system or a whole home heat pump system. We'll talk about different kind of control strategies as well. That's kind of promoted by the utilities. And then after we get through that section, then we're really going to highlight some of the difference between like the Asian heat pump manufacturers, or in other words, like mini split style heat pumps, as well as the US manufacturers, and just make sure that everyone's kind of familiar with some of the pros and cons of each. So yeah, let's take it away. So the first thing that we'll talk about is just like a fireplace. So if we roll back the clock about 200 years, how most people were heating their homes in New England was just using fireplaces. And energy moves in 3 different ways. It moves via conduction, which is things touching one another. It moves via convection, which is through the air or through a fluid. And then it also energy can also move through radiation. And that's really kind of line of sight. So do know with the fireplaces, the vast majority of the conductive energy and the convective energy is not captured by this device. So with what a fireplace would do, it would just radiate its heat out into the room, but the vast majority of the heat is going straight up and out the chimney. So if you were ever trying to heat an entire home with fireplaces, you wouldn't have like one central fireplace. You would need multiple fireplaces, and you'd need to be tending to multiple fires throughout the day. And it was wasteful and time consuming. So people were trying to come up with something better. And the better thing that they created was like a wood stove. And the big thing with a wood stove is it gets that firebox out of the chimney, which allows for convective loops to happen. So if we were following my mouse, let's say cold air is denser than warm air is more buoyant than cold air. So what would be happening over on the floor is that there's like dense cold air. As you're heating up the wood stove, it's going to heat up the air that's below the wood stove, and it's going to make it hot and buoyant. So that air is going to rise up, and it's going to displace or push kind of the air that's already up there away. So what ends up happening when you have a wood stove is it does create these natural convective loops going on inside of the room, which just helps extract more heat or more energy from that actual wood stove or through the firebox inside of it. Now via radiation, instead of it just radiating out in one direction, now it's radiating out in 6 different directions. So like behind it, in front, left, right, top, bottom, like everywhere is radiating out from it. So it's just going to make the space feel a lot more comfortable. Oftentimes with wood stoves, there's enough heating capacity or heating horsepower to be heating an entire home. But as you get further and further away from the device or from the appliance, it's eventually going to become colder and colder and colder. And for some people and for some homes, that at some point, that may be on the threshold of uncomfortable. As I'm thinking about, say, like a ductless mini split, I'm thinking that in all practice, it's the exact same level of comfort that a wood stove would provide. However, oftentimes at smaller capacities. So with kind of the smallest, like the largest residential ductless mini split is around 30,000 BTUs per hour. So on paper, hypothetically, a wood stove could have more heating capacity or more heating horsepower than a single ductless mini split. But it really is like the same achievable level of comfort, like with just one unit, and it's just going to be dumping heat in the space. It'll also be removing heat from the space in the summertime. But yeah, it's a perfectly acceptable way to heat. And same thing with a ductless unit. It's a perfectly acceptable way to heat for some people. But it is important to know that there's a reason why people invented what comes after that, which is, say, a central heating system. So the first type of central heating system that we're going to talk about is a steam boiler. And a few, I guess, fun facts with the steam boiler. So what happens with a steam boiler is, like, one, it was invented before electricity. It was also invented before thermostats were invented, okay? But what's happening over here is there's really just kind of a pot of water sitting inside of this appliance. Fire happens underneath it, and it's going to turn that pot of water into a gas, into steam. The steam is going to rise up through the pipes, and it's going to go into a radiator, which we can look at in a second. And then that hot gas, which is a 212-degree gas, gives off its energy to, say, a 68-degree room. And what happens is that gas, which switches into a liquid, and it drops right back down the pipe that it came up in, to get reheated again and again and again. So I'm going to just switch my camera, and we're going to just go and look at what this can actually look like inside of a home. So down in the basement, we're going to have something called a boiler. So inside of the boiler is going to be a basin of water. There's going to be a fire underneath it. And what's going to happen is this fire is going to be heating up this liquid water until it becomes a gas. Once it's a gas, it is going to be going up through a pipe, and it is going to go over into every room inside of the house. So let me just click. Okay. So every room inside of the house is going to have something called a column radiator. And a column radiator, I'll show you guys in just a second. But let me just finish drawing this out. So we have radiators, and we need one more line over here, radiators, and I'll put a radiator over here too. Okay, so every single room in the house is going to, say, have one radiator. And this is really important because when this system was invented, was before insulation was invented, okay? So when this system was invented, it was before double pane windows were invented. So this home is going to have a very high heat load, and because of that, it's going to be needing a radiator in each and every room. As we do think about this system and we think about what it's doing, so it switches this liquid over into a gas. The gas goes into the radiators. It's going into there at 212 degrees, and it's filled with energy because it has all of the latent energy that made this water into a gas, or this liquid into a gas. The room is, say, 68 degrees. So what happens is hot goes to cold. So this 212-degree radiator is going to be transferring its heat into, say, the 68-degree room until this becomes, say, 211-degree water. And what happens between 212 and 211, it switches between a gas over to a liquid. And so now that it's a liquid, it just goes pretty much back down the same exact pipe that it came up in, and it just feeds right back into the boiler to get reheated again and again and again. Because everything is tied to, say, this like central steam distribution system, there's no zoning. So you're going to have, say, one thermostat on the wall and on the first floor. And what ends up happening is when you set this thermostat to 70 degrees, this boiler is going to fire until this thermostat is at 70 degrees. This thermostat has no idea what's going on in this room, this room, this room, this room, that room, that room. It's only measuring the temperature at a central location. So say, for example, that you're putting in a whole home heat pump system. You would likely, if it's this type of a setup, you're likely thinking about putting in, say, potentially 7 ductless mini splits if the house is performing the same way it did 100 years ago when this system went in. Okay, because it likely is going to have a big enough load that it's going to need that much equipment. However, say if you have buttoned up the home, it's likely that that load would have been cut in half. So instead of needing, say, 100,000 BTUs per hour, maybe you're needing 50,000 BTUs per hour. And then maybe it's much more appropriate to have, say, a ductless unit here, 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 and here. Or alternatively, maybe you would be thinking about putting in a ducted system down in the basement and a separate ducted system up in the attic. So if there is a steam heating system, do know that there's lots of ways to go from steam to whole home heat pumps. When things get tricky is with talking about ductless and thinking about partial home, because say that you wanted to, because the second floor always overheats, and it always overheats because it's being controlled by a thermostat on the first floor, and the house has been buttoned up. You may be thinking like, all right, let me go and I'm going to put in a central heat pump up in the attic and duct down to all the bedrooms. And that way the heat pump could be, say, doing my second floor, while the steam boiler is doing my first floor. You're going to need, say, an exception from Mass Save to make this partial home solution work. The good news with, say, steam radiators is every single steam radiator has a shut-off valve. So it's very easy to take a room that's being covered by steam and making it completely covered by a ductless mini split or by a heat pump. When, say, with a forced hot water system, which we'll talk about in a second, instead of each radiator being plumbed independently, the radiators may be plumbed on a circuit. So the hot water is going into this radiator and then going out of this radiator and then going into this radiator and then going out of that radiator and into this one and out of that one. So it'd be a circuit. So you can't just turn off, say, this radiator, because if you turn off this radiator, then all of the other radiators on that circuit are no longer going to work. And then, say, for the first floor, if you are just thinking about ductless or a partial home solution, do know that there's nothing wrong with, say, putting in a single ductless unit or 2 ductless units and using that as your primary, putting on an integrated control and just knowing that warm air is hot and buoyant, and the heat, if you're conditioning the first floor, you're always semi-conditioning the second floor. So no problem with integrated controls for doing first floor with steam, but for second floor, it does get a little trickier. Let me pause there. What questions may you have about steam heating systems or steam distribution systems?
This is kind of a weird question, but why do some people really love steam?
Yeah, I think that it's the same way why a cat likes a sun patch from a window. People just like really hot things. Yeah. So there is something that's very nice about, say, having a heating element that's 212 degrees all winter long in the room that you're in. So it's the hottest, without a doubt, form of heat that you can really have throughout an entire home, where just the emitter is blazing hot, scalding hot, unsafe for children without a cover in their bedroom hot. why I think I like steam, some like cool things about it. It's like the same thing that's like cool about like seeing like a 100-year-old locomotive. Like it's a marvel of engineering that like people came up with this 100 years ago. It's in most steam systems, like the components of it are in traditionally like remarkable shape for being 100 years old. So like really on every single like residential project, it was like a real engineering feat miracle. Reasons why people don't love steam heat is like 100-year-old homes have typically settled, and for kind of hot gas to make its way up and liquid to always be making its way back down with a house that may have settled like 6 inches or a foot on one side over time often causes a imbalance in the piping. So you're now having gas trying to come up and water coming down, and things are not flowing and they're butting up against each other, and there's banging and clanging and hissing and spitting. Reasons
that actually brings up a different question, which is it really is the same pipe that the gas goes up and the water goes down.
Yeah, the vast majority of residential steam is called one pipe. And hold on. So there's okay, so that's the one pipe. And you close that if you want to shut off the radiator. There's the radiator. And then it has a valve right over here. And that's what lets the, as this heats up, it pushes the air out of it. And then the steam will then fill it. And then as the steam condenses inside of here, the volume of air shrinks. So then this kind of sucks air from the room back down into it. So this is like kind of like the lungs of the system. And do you know with steam systems that sometimes with this valve, this pops up, it's user changeable, but you can adjust how quickly or how much air it lets out of here, which slows down or speeds up kind of the rate that this radiator will warm up. But yeah, one pipe steam is by far the most prevalent type of steam heating system. In like, say you have a 4,500 square foot, 100-year-old home, it very well could be a 2-pipe steam system where there's a kind of a component that's kind of pulling the gases through one radiator to another. But yeah, for the most part, it's one pipe. I did simplify the diagram down in the basement with kind of the piping that's going from coming up from the boiler and back down to the boiler. But for each radiator, it's just one pipe. You can shut off each radiator independently. But yeah, it's another thing that's nice with steam, say if you lose electricity, you still need electricity for all of modern steam boilers, but they're extremely easy to power with say Tesla Powerwall or even a gasoline powered generator. So with steam, you're not using electricity to move the heat from the basement to the home like you would be with, say, a furnace or a forced hot water boiler. So they're very, very, very easy to run off of a backup power solution, which is like a nice thing for like resiliency and redundancy. And it may be a reason why someone doesn't want to be ripping out their radiators. One additional thing with steam is oftentimes decommissioning a steam heating system is also an asbestos abatement project. So I would say that for most people who are trying to decarbonize or electrify the home, I wouldn't likely be talking about ripping out all of the radiators unless it's like a very tight space, and that additional floor space would be really nice to have. Just because oftentimes once you start taking out radiators, you're going to be stumbling into asbestos somewhere along the project, and that's better just to leave in place until like the home's getting like a much more thorough remodel. All right. All right, so the next one, and I'm going to touch on this one, but we're not going to do a diagram on this, would be kind of the first generation of a furnace. So with the steam boiler that was heating up water down in the basement and is heating it up so much to turn it into a gas. Over here, this is just using a appliance to be heating up air. So the first generation of this was also invented before electricity, just to put some context to this, and it would be called a gravity furnace. And off of the top of this appliance would be, say, ductwork, and all of the ductwork could be coming, say, directly off of the furnace, or maybe they're doing what's called a plenum, like kind of a trunk, and then they're doing all of the ductwork off of the trunk. But this whole thing was working without any electricity, and what there would be somewhere on the first floor would have just been more or less a grate or a hole or a vent in your first floor. And then they would just be connecting ductwork also back down into the basement, into this furnace. And this is just heating up the air. So cold, dense air falls down into that grate and then into the furnace. And their combustion is taking place. It's warming up the air, it's making it hot, it's making it buoyant. And then all of that warm air is traveling up into each of the different rooms. This originally worked actually pretty well because this was also invented before people were using natural gas or petroleum, home heating oil, propane. And over here, you would just have this long, continuous simmering wood fire or coal fire. And you would just be in the morning, someone would be shoveling coal or wood into the unit, and then it's just this like long continuous burn, and that long continuous burn worked perfectly fine with just working with natural convection. Once people switched over to say like home heating oil or natural gas or these extremely energy rich fuels, there was so much heat extracted in the combustion process that it was just instantly 500 degrees and then like off. And that didn't work well with this type of distribution system. So then they started putting fans in these. And that's why we now call this type of a system forced hot air. The forced is incorporating a fan into the system. Once again, once they put thermostats on these things, there would be no zoning. So just be one thermostat centrally located on the first floor. All of the same challenges with steam in terms of like mass save, partial home rebates. How are we doing first floor versus second floor? Okay. So now we have forced hot water. So this is another form of a boiler. So before we looked at a very ancient steam boiler, do you know that a modern steam boiler looks very similar to this as well? So not all boilers look like they're 100 years old. I love this photo of the boiler because we see what's called the aquastat temperature, which is at 180 degrees. And 95% of all forced hot water systems in Massachusetts are probably set at 180 degrees. Where is the pipe insulation? Nicole, that's a great comment. Yeah, do you know that pipe insulation's a funny thing in the States because like no one does it, and it is wildly important, and it's especially important with steam because if you don't insulate the steam pipes, the gas doesn't stay as a gas. It condenses somewhere in the basement or somewhere along your walls and it just drops back down into the boiler and it never actually gets its way into the radiators. But with forced hot water, pipe insulation is a really great idea because instead of heating the spaces that you're not using, all of that energy inside of the pipe could be heating up the spaces that you do want to heat. So pipe insulation is always a very, very good idea. Oh, so thanks for the comment, Nicole. But the forced hot water boiler, so this is set at 180 degrees. So let's just focus in on that number for a second. So the 180 degrees is what is likely going to every single baseboard, every single radiator in the vast majority of homes in Massachusetts. The only time that you ever see plumbers not set the aquastat to 180 degrees is if they have like radiant floors or a hydro air system, which we'll talk about in a moment. The problem with this and why I keep talking about 180 degrees is air to water heat pumps are real. However, they are looking to put out a water temperature between say 90 degrees and 140 degrees. And the closer you are to 90 degrees, the equipment becomes much more efficient. So most of the time, if say the home was properly designed for 180 degree water, they did an accurate heat load calculation, they put in baseboards for 180 degree water. If you go and put in an air to water heat pump, that is not going to sufficiently heat the home. However, let's say that this boiler is in a 80-year-old home, there's baseboards throughout the home, and they've gone through a deepish energy retrofit. It's likely that this temperature could be way, way lower because the load has gotten way lower. Then, if you adjust the aquastat and you get through, say, winter number 1 with 140 degree water, then you could feel very good about adopting an air to water heat pump system. So just going on to some of the components or controls over here that are worth highlighting is, so with a boiler, they always are going to require electricity. And why this one's requiring electricity is because there's a oil burner that's attached to it. And I can see it's being wired with 110 volts of electricity. I also see this, which is a circulator pump, and that's going to be pushing and pulling the 180 degree water throughout the home. I also see off of this boiler a hot water heater cylinder, but I don't see any combustion taking place on here. So on the boiler, I see a flue pipe, which is what the exhaust gases are going into. Over on the domestic hot water heater, I don't see any of that. And the reason for that is they're using this boiler to also be heating up their domestic hot water. So this boiler is providing a zone of heat for, say, the first floor, a zone of heat for, say, the second floor, and separate zone of heat for the indirect hot water heater. So one nice thing with a forced hot water boiler is one appliance can now do multiple things. So let me just pause my screen and switch my video, and let's just highlight what this could look like. So down in the basement, once again, we have a boiler, and then there's once again like a pot of water sitting on top of it. But what we'll have is there's going to be multiple zones off of this. So I'll have zone 1, and then I'll have zone 2, and then I'll have zone 3 as well. So for zone 1, what that could be doing is that could be going to, say, baseboards on the first floor. So water is going into this baseboard and water is coming out of this baseboard. Water is going into this baseboard and out of this baseboard, into this baseboard and out of that baseboard, and back into the boiler. This zone is going to be connected to, say, thermostat number 1. For zone number 2, baseboard, 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 and then back down over to the boiler. And zone 2 is also going to have its own thermostat. Say that you put on an addition. With the addition that you put on, off of the boiler, you could have zone number 4. And then on zone number 4, could have another baseboard over here connected to another thermostat. So with this one home, you could have, say, 3 different heating zones. In addition, you could also have a zone for your domestic hot water. So in some ways, it's kind of elegant that you can have one appliance doing multiple things throughout the home. Additionally, a, say, reputable plumber could, instead of putting in a baseboard at 180-degree water going into, say, this addition, they could be putting in radiant floors going into this addition with 120-degree water by using a mixing valve. So there's even flexibility in terms of the type of emitters that are being used inside of the project. Sue asked the question, if you set the boiler at 140, would that not give you enough heat for the hot water tank? So for domestic hot water, we're always, the goal is to be getting 120-degree water at the outlet. So there's no problem with having, say, like a low temperature hydronic distribution system and maintaining enough domestic hot water. And then the other thing, even with the boiler, is let's say that you did have you want your radiant floors set at 90 degrees and you wanted your domestic hot water to be at 120 degrees. Then it would just be the zone going over into the radiant would just have a mixing valve. So no problems there. In fact, some people who do low temperature hydronics, instead of putting in a whole boiler, they're just doing everything off of like residential domestic hot water heaters. So sometimes that appliance can actually be your heating system in low-ish load homes. Any questions with boilers? Forced hot water boilers. That's gracious. There we go.
Is there so it's just a matter of like whether you have enough baseboards to meet the load at the lower temperature? Like there isn't, are there baseboards that really don't function down to 140 or 120, or is it entirely a matter of having enough?
All right. Yep, that's a great question. So let's just go over and we'll just go to slant fin BTU. Okay. All right. Just to confirm, everyone can see a PDF that has a bunch of numbers on it. Okay, thank you. All right, so let's just go and look at, say, with the baseboard, what will happen. What happens when you have different temperature water flowing through it. So say if you have 180-degree water and the circulator pump is pumping water through the system at 1 gallon per minute, what would end up happening is for every linear foot of baseboard that you would have would provide 570 BTUs per hour. So if you have a room with, say, 10 linear feet of baseboard, that is going to provide up to 5,700 BTUs when the per hour when the thermostat is calling for heat. If you go and rip that out and you put in, say, a air to water heat pump, and you're putting water through the system at 140 degrees, which is the least efficient temperature that you can run like an air to water heat pump system, then it would provide 3,000 BTUs for those 10 linear feet of baseboard. So it's not that you can't do it, it's that you need to go and look at each room, figure out what the actual heat load is, and then kind of size down the performance, size down the BTUs based off of the water temperature that's going in, and then thinking like, is this safe or is this risky, and how low can I set the air to water heat pump? But if the home was, say, built and the equipment was like designed and commissioned and installed correctly, and they put in the right amount of baseboards for the home as is, and someone didn't make any changes to the thermal envelope, I can guarantee you and say that like you can't put in an air to water heat pump and just like cut the emission in half. So yeah, so that's like all of this stuff is visible. A reputable plumber can kind of do the math and say like safe, not safe, risky, not risky. But it definitely has some challenges. But do you know that there are different types of baseboards as well, including like low temperature hydronic baseboard. And with that, you could be putting water through it at 120 degrees, but it could be putting out 600-ish BTUs per hour because there's so much, there's more heating elements on it, or there could be a fan that's assisting in speeding up the convection. So yeah, so hopefully in the coming years we'll see a lot more kind of savvy contractors with this savvy contractors who are able to think critically about what it will take to actually electrify homes using the existing forced hot water distribution system. But right now there's not a lot of people doing it. And we'll talk more about hydro in just a moment. I don't want to overwhelm you too much. Okay. So now we have a modern forced hot air furnace, and let's just go and look at a few different things because some things have changed that are worth highlighting. So over here, the flue pipe was metal, and if I were to measure the temperature of these exhaust gases, they'd be somewhere around like 350 to 500 degrees, which I just think is remarkable because lots of households argue between, say, 68 degrees and 70 degrees. However, I can assure you that if you have a heating system that looks like this, you have hundreds upon hundreds of degrees that are just going up and out the house through the chimney. So do know with a traditional fossil fuel-based heating system, there's a lot of inefficiency with the fact that it's just venting into a chimney and hundreds of degrees of energy are not being captured by it. So we're now seeing our first like high efficiency system, and how I know that it's high efficiency, instead of having a metal vent pipe, it's a plastic vent pipe. And if you were putting 350 or 500 degree gases into a plastic vent pipe, it would instantly turn to goo. So this is high efficiency. Other things that I see over here is I see ductwork over on this side, and that's the return ductwork that's sucking the air back in from the home. When I think of a modern gas furnace or a modern oil-fired furnace, I really think of it as like a 3-drawer filing cabinet, where the bottom drawer would be the blower. The middle drawer would be the combustion chamber. In this top drawer would be the coil that's tied to either a central AC or a heat pump system. So with just looking at this American standard furnace, I don't know if this is a heat pump or cooling only, because with both of those devices, it's just a metal box that's sitting on top of a fossil fuel-based furnace. Okay, so I can see that this has an insulated refrigerant line and an uninsulated refrigerant line, which makes me think that it's an AC and not a heat pump. But do know that this box over here, that's the heat pump solution from like all US manufacturers. It's really just a coil that sits on top of a fossil fuel-based furnace. Other things that I see with this furnace that are worth highlighting or noting is over here, I can see this compartment, which in most instances is usually located lower. but that would be a robust air filter, which is great to see because you can never have too good of indoor air quality. I also see this Honeywell thing right over here in this zone panel over here. And this zone panel is talking to this supply and this supply. And what's neat about this is each of these dampers are connected to the zone control, and it allows for this one furnace to have two thermostats on it. So let's say we could have first floor with its own zone, second floor with its own zone. So these dampers can open or close independently to let the hot air or the cold air just get to the spaces that is actually needing it. So this is a very nice improvement over the previous furnaces where the entire home is likely all just one zone. I think that zoning makes a lot of sense anytime you have more than one story or floor. It should have its own zone, or alternatively, if there's ever a room that is performing differently because of architectural reasons or design build reasons, that should also have its own independent zone. So say that you put on a brand new addition and you spray foam everything and you run ductwork into that space is going to be performing wildly differently than the original portion of the home. Say you have a room that's above an attached garage, performing wildly differently than the room above a semi-conditioned basement. So zoning makes a lot of sense for forced hot air furnaces anytime that there's different characteristics with that space. Other things that could be going, well, I'll talk about humidification a little bit later, but any questions with forced hot air furnaces? Would it be valuable if I draw this out, or do you think that you understand kind of the core concepts? Okay, one additional thing that I'll just mention with a forced hot air furnace, can you zone central heat pumps? Yes. So Jillian asked, can you zone central heat pumps? Yes, it's way easier with the US equipment than with the Asian equipment, or there's less consequences, but we'll touch on that a little bit later. But yes, hypothetically, you can zone central heat pumps. Sometimes if it's a mini split style heat pump and you're zoning it, you're going to prevent it from modulating, and it may just run as a single stage equipment, which brings down the efficiency and may slightly bring down the comfort level. But there are third-party zone controls that do play well with mini split heat pumps. Okay. Cool. All right, so now we're on to modern hydronics, and I cropped this photo in kind of a poor way. Shoot, I'm not going to fix this. Hold on one second. Let me just try and drag that over. I should fix it just so you can see what. Oh shoot, hold on one second here. Share, good. Okay. I'll fix my screen sharing in a second. All right, so the now this is a high efficiency boiler right over here. So with this boiler, it would be venting out through a PVC pipe. I can't see it in this photo. I can't see it in this exactly where the venting is on this photo. But it'd just be a PVC pipe going out and a PVC pipe coming in. So fresh air is being brought in from the outside for combustion. Combustion's taking place inside of this box that's hanging on the wall. And then so much heat from the exhaust is pulled out of it that this thing is going to be, say, anywhere between 90 and 97% efficient. What's nice with these wall hung boilers is they free up a ton of space. They can also be used for doing instantaneous domestic hot water. So we'll talk more about on-demand hot water heaters in a bit, but it's pretty much unlimited domestic hot water unless you exceed the maximum flow. So you could be filling up a 100-gallon jacuzzi tub time after again, which is nice. But with modern hydronics, some of the things that's nice about it is you can have lots and lots of different zones. So so you could, every time that I see this thing over here, which is a circulator pump, that would be its own zone. So it could be like each room has its own zone, or each room has its own radiant floor is tied to its own thermostat. So there's like tons of flexibility. This is like, when you look at it, it's looking like a circuit board. It's super duper clean. It's doing your domestic hot water. You can be having baseboards, radiators, fan coils, so like lots of different emitters. But with modern hydronics now, it's really like a new construction. Boilers are really only going in on like expensive homes. So no one who's a production builder is doing boilers anymore. It's really kind of now more about like high-ish and niche, or alternatively for hydro air, which I'm going to now talk about with switching my camera over. Screen share, stop. Let's switch. Okay. So hydro air is this. So you have a boiler down in the basement, and then we have the basin of water inside of it. And for our hydro air setup, we're going to have two different zones. So zone number one, it's going to be hot water coming out of the boiler and hot water going back into the boiler. And it is going to be attached to a hydro air handler. So what that looks like, it's going to be the same as like that 3-drawer filing cabinet. So the bottom of the drawer is going to be a fan. The middle of the filing cabinet is going to be a hydronic heat exchanger. So hot water flows into this coil and warm water flows back out of that coil. And then on the top of the unit is going to be either a heat pump coil or an AC coil. So that's going over to an outdoor unit. So and then we're also going to have return ductwork that's going to be sucking air back into the system. And off of the top of this, we're going to have supply ductwork that's going to be blowing air out of the system. So when you are, say your home is 67 degrees and you're wanting it to be 68 degrees, what's going to happen is the thermostat is going to tell the boiler to fire. The boiler fires and it heats up water, and then that water is going to flow over to the hydronic coil inside of the hydro air system. Then the blower motor starts going and it starts sucking in air from the house, blowing air up over the hydronic coil. And then that forced air is going to blow into, say, the living room, the dining room, the family room. Additionally, there's a separate system that would be up in the attic. And then you're having supply ductwork blowing down over there. And then you would have, say, a return ductwork that's sucking air back in. There's a blower motor. There's a hydronic heat exchanger, and then there's also an AC or a heat pump coil. And if you're upstairs, you like to sleep with it, say 72 degrees, and the space is only 71 degrees, the thermostat would tell the boiler to fire, start sending hot water over to the heat exchanger up in the attic or the air handler up in the attic. And then the blower motor would turn on. It would start sucking in, say, the 71-degree air up in the attic, and it starts blowing out hot air until that space gets to be 72 degrees. In the summertime, instead of the boiler firing, the air handlers are just going to be communicating with the outdoor heat pump system or the outdoor central AC system. If they do put in a heat pump in the wintertime, instead of the boiler needing to fire to provide heat to the air handler, the heat pump could be doing it. But typically with these HydroAir systems, they're configured to equipment from US manufacturers that is going to be needing the boiler for extreme cold weather. There's a real argument or real thought when you're working with someone who has HydroAir of whether or not they should drop the boiler, don't pursue equipment from US manufacturers, simplify the mechanical complexity, and just put in a central heat pump system without a capacity drop. So with HydroAir, I typically find that consulting on these projects is a bit trickier, just because there is kind of this question of like, how much of the mechanical equipment are you abandoning? Any questions with HydroAir? And just an additional thought with HydroAir is like, it may seem like it's complicated and like, why would anyone ever choose this? But it's a lot more elegant to be, say, putting in a HydroAir system with multiple air handlers than it would be to be running gas lines throughout the house. So putting in a gas furnace up in your attic is a lot riskier, I would say, than putting in a HydroAir system up in the attic, because eliminating combustion shrinks down gas lines, which is always good. And then the other thing is now you don't have to deal with venting that appliance in traditionally an unconditioned space. Some things that's nice as well with moving away from HydroAir is oftentimes equipment is outside of the thermal envelope and it's using water as the heat transfer mechanism, and freezing is real and pipes bursting is real. And the alternative is to use glycol or antifreeze versus water, but that does take a kind of a greater toll on all of the equipment than just using water. So like the circulator pumps get gummed up, pressure reducing, there's just a lot of components that are less happy being surrounded by glycol than water. Okay, so I was just reading through the comments and Jillian wrote, with the previous system, all I can think of all the things that can go wrong, so many components. And I do think that some of this sentiment is true. One of the things with say a modern hydronic system, though, like with this photo, is like everything can be isolated and easily changed up. So one nice thing would say with putting in, say, a boiler like this, is that the distribution system and the heating system are somewhat independent. So say if the boiler goes bad, they're literally disconnecting gas valve, supply line, return line, electrical, pop that thing off and pop a new one on, and then kind of all of the plumbing and all of the controls are all downstream from the unit. So it really is much more of it's like kind of independent systems versus say with a ductless mini split, if something goes wrong, then you may be, or it becomes end of life, you're pretty much throwing everything in the trash. And even with most HVAC installers, they don't say trust the line set that's been exposed to the New England elements for the last 15 or 20 years. So one nice thing with putting in, say, a hydronic system or a forced hot air system is the distribution system and the heating engine are really two separate components, just like say the same thing with like an automobile. Different components working together is what's making up the system. But yeah, and I think the other thing too, it's like with plumbing, if something's to leak, it's likely property damage. With a heat pump, if something's to leak, there's not going to be property damage, but there could be a refrigerant going out into the atmosphere that is significantly high global warming potential. So they all have their pros and cons. But with me and looking at this, it'd be like, well, that'd be something that I would like in my house. With traditional boilers, so another thing that we didn't talk about with the high efficiency boilers, like any of the high efficiency equipment, the expected lifespan of it is like 15 years. Same thing with the heat pump. We should be setting expectations about 15 years. With the older equipment, the life expectancy of it's closer to 30 years. And the reason for that is this is all just made of like cast iron and steel. And it is a very inefficient heat exchanger. But with the new stuff, it is a very, it's all like finely machined stainless steel and aluminum, and it's much more, it's a lot thinner, just physically, it's like thinner. So it does have a likely higher chance of failing, say within 15 years versus the older equipment closer to 30 years. And then the other thing that's nice with the older equipment too is like you can put on any circulator pump, any like gas valve, oil burner, like the parts are interchangeable. But with a lot of the newer equipment, all of the parts are very proprietary, where it needs to be like fitting inside of a cabinet. So there is the people there's definitely a lot of plumbers out there and HVAC people out there that prefer kind of the mid efficiency equipment over the high efficiency equipment with just the lifespan of it. But plumbers, some reasons why people like the high efficiency stuff is like, one, you put it in and then the customer experiences lower energy costs. Two, it's a lot easier to install, like just physically like getting it into the space. And three, with the high efficiency stuff, it really does need annual maintenance. So it often can also be promoting service contracts, and then that's also going to become rebate eligible. So no right or wrong with any of this stuff, but that's kind of where we are right now in terms of the market. I just want to briefly touch on electric heat. So with electric heat, this could be baseboards, and sometimes these electric baseboards are tied to a thermostat that would be in the same room that these electric baseboards are in. So typically with electric heat, it will be multiple heating elements that can be controlled independently. Some very cheap electric baseboards, instead of being connected to a thermostat, just has a temperature dial on the unit that could be low to high, and it's just a dial and you put it wherever you want to put it. The hardwired electric baseboards don't use electricity any differently than an electric space heater would. With all electric space heaters, some of them may feel a little bit different with the type of heat that they provide. So some of them may have a fan, some of them may be on wheels and look like a column radiator, but it's all the same thing. 1 unit of electricity in, 3,412 BTUs out. So all of them is like 100% efficient. But unless you live in a MLP town with very good rates, electric heat is oftentimes extremely expensive compared to all the other options, because as you are buying a kilowatt hour, you are buying all of the inefficiencies of the power plant, all of the inefficiencies with today's grid, and you're not getting that magical COP or multiplier that you would with a heat pump system. For ductless mini splits or ductless air source heat pumps, typically the range of this equipment is between 6,000 all the way up to 30,000 BTUs. For all equipment, we should be hoping at a coefficient of performance of greater than 200% over the year. The equipment modulates to meet the exact room load. So what that means is it doesn't turn on and off like all of the traditional systems that we've looked at before. It just figures out what the load is of the room and it dumps in the appropriate amount of heat and it just runs continuously. The cold climate equipment without a capacity drop is market ready. It's been used in other regions of the world for a number of years. No combustion's taking place. And if you have on-site renewables, you could be pairing the on-site renewables with the heat pump and becoming a definition of net zero, which is cool. We also have ducted air source heat pumps. So with ducted air source heat pumps, we'll look a little bit more at this, but do know that there's subcategories within this category. So there's the US equipment, there's the Asian equipment, there's the little units called like low static, there's medium units called medium static. Also, those two could be also referred to as slim duct. That's sometimes a vocab that installers will use. And then there's high velocity systems, which look exactly like a fossil fuel based furnace, but no combustion's taking place. The ducted heat pumps traditionally look really, really, really good when you're connecting them with an energy monitor. So the nice thing with the ducted heat pump systems, especially when using it for a whole home, is it has a huge volume of air and it allows the heat pump to likely run at its peak efficiency for the longest periods of time. Versus with ductless units, where oftentimes they're in a room and it gets the room to the set point temperature and then cycling can be happening. So ducted air source heat pumps, as long as the budget allows, is usually the right way to go when people are trying to electrify. Sorry, something came in chat. Is the thermometer in unit can be placed anywhere? Okay, so Justin asked a question about for ductless units, where the thermostat is located. And this will tie a little bit with integrated controls, but over here is a ductless heat pump. And sitting right on inside of the top of the unit is a thing called a thermistor, which is the internal thermostat of it. As I take my handheld remote and I go from 70 degrees, I don't know if you heard the click, up to 72 degrees, I just blasted over a command to the unit to change the algorithm inside of it to try to take a guess at making this room temperature 72 degrees. There is no thermostat located inside of this remote. So if I put this remote on the other side of the room to try to get that side of the room exactly at 72 degrees, it doesn't do anything. There are thermostats from each of the mini split manufacturers that instead of doing an algorithm inside of the unit, it would read the temperature at the wall. And based off of the temperature at the wall, that would be informing how hard that heat pump needs to be working to get that set point satisfied. So oftentimes when people are designing a heat pump system with a, say, single zone ductless mini split or a handful of ductless mini splits, I'm often recommending a wireless or wired thermostat to ensure that the zone is going to become as comfortable as someone wants it to be. Because otherwise, like, warm air rises if that system's on the, on the top of the wall in a big space. It very well could be getting that space to say 70 degrees or 72 degrees, but it really has no idea what's happening on the other side of the room. So hopefully that answered that question. Okay. So this is something else that you should be aware of. It's called a high velocity system. And with high velocity, what's going on is a forced hot air system. And instead of using traditional ductwork, it's using ductwork that can be that's 3 inches in diameter. And the reason why this is a great idea, or it's like good that it exists traditionally, has been that there's lots of homes where you can't fit through like a 8-inch duct or a 10-inch duct. So some people who have older homes that were trying to retrofit them for central AC would be doing a high velocity system. So instead of having kind of like a standard register, it's kind of these hockey puck sized vents that would be scattered throughout the ceiling, or say scattered throughout the floor. The problems with hydro air are this in terms of heat pump. So this is a unit from SpacePack. And this has been retrofitted to be communicating, or this was installed to be communicating with, say, a Bosch heat pump system. The Bosch heat pump system, if it's tied to a traditional air handler or tied to a traditional encased coil, is going to qualify for Mass Save rebates, for federal rebates. It'll be Energy Star certified. But because we're trying to push air through these teeny tiny ductwork, it needs a really, really strong blower motor. The blower motor uses so much electricity that any measure that we use in terms of SEER or HSPF to think about equipment efficiency, it uses so much electricity that it misses those marks. So do know that with high velocity systems, it could be tied to a great heat pump, but the blower motor is going to use so much electricity, it's not going to qualify for any rebates. Other things that's true with high velocity equipment is the ductwork often doesn't, just because the ductwork is these like flexible tubes, it doesn't appear that it's often well designed. So it's snaking around, it's pinched, it's crimped. And that's been my experience as an auditor, as well as consulting with people who have existing forced high velocity systems that have been their primary cooling system or heating system. With high velocity, it could also be tied to hydro air. So there could be a hydronic air handler, hydronic coil inside of it. But this exists. People can be swapping this straight up for a heat pump, but it's not going to become rebate eligible. Cool. So we're now going to kind of get into a little, it's a little technical, but I really want to highlight some of the difference between the US and the US and Asian manufacturers about understanding the difference in performance with a central heat pump system versus like a ducted mini split or a ductless mini split. So on the US side, we have a few different manufacturers that are common. So like Bryant, Lennox, Trane, Carrier, American Standard, Bosch, are some. And then on the Asian side, the biggest ones is like Mitsubishi, LG, Fujitsu. There's a handful others like Gree, Haier, Cooper Hunter, but they all make the mini split style heat pumps. As far as visually understanding the difference between the two is like with the US equipment, it's all like top discharge. With the Asian equipment, it's all side discharge. So if you wanted to like, even without seeing any of the brands, if I went to the outside of a home and I saw something that looked like a traditional central AC that was a heat pump, be from a US manufacturer. If I see something that looks like this, it's going to be from an Asian manufacturer. It'll be a mini split. It'll likely have very similar performance. Some of the benefits of the two different types is, so say with like central heat pumps, they can run at multiple stages. So it could be low or high, or it could be low, medium, and high. With this type of equipment, you can put on Honeywell zone control and can have first floor, second floor, third floor, all independently heated from this one unit. You can have dual fuel integration, where you can have a high efficiency heat pump that's sitting on top of a natural gas or an oil fired furnace. It could be tied to a hydro air system. It has a rich legacy of third-party ecosystems. So with the controls, it can be talking to any thermostat, any humidifier, any dehumidifier. You could have really robust air filtration, easy compatibility with ERVs or HRVs. The big thing in terms of like electrification and decarbonization with this type of equipment is it does have a capacity drop. So it's really hard to use this type of equipment and it being the sole source of heat in the home, unless it's using electric resistance, which for the vast majority of homes in Massachusetts is likely not a great idea. For the mini split types, it's variable speed or modulating. So it runs in low and it runs in high and it runs everywhere in between. If you want to have zoning, typically the answer is put in an additional piece of indoor equipment. Okay, so instead of dealing with like a zone controls and dampers, the best way to do it is typically putting in a separate unit that's dedicated for the space that has different architectural or thermal characteristics. The controls of this equipment are proprietary. So the same thing as like a laptop versus a desktop. With a desktop, you can put in like or kind of rolling back the clock, but you could put in like whatever graphics card, whatever sound card, whatever power supply you want. Like that's all a reality with the desktop computer, but the laptop computer, it's all like you need the specific like Wi-Fi module that Lenovo makes or Apple makes if you wanted to change your Wi-Fi because the previous one was broken. So with mini splits, it's all very proprietary, the ecosystem. This type of equipment could be sold without a capacity drop. So Mitsubishi calls it Hyperheat, LG calls it Red, Fujitsu calls it XLHT, but all of the major manufacturers have a type of mini split heat pump that doesn't lose its heating capacity. Another thing that I'll just highlight is there's also dry mode with this type of equipment. And with dry mode, what it does is it just takes slows the blower motor down to its lowest speed and it keeps the coil inside extremely cold. And that does a really good job of removing humidity while not pulling so much heat out of the space. So, with mini splits, some people really like dry mode. Actually, give me 1 second. I meant to put something else in chat too. Okay, so in chat, I just put in a link again to the capacity balance point calculator that I use, but I'm also putting in a link to airsourceheatpump.neep.org. And when you go over to that website, it will bring up the NEEP database where you can go search for any piece of equipment and go and look at its performance. I could have pulled any piece of equipment to tell a certain narrative, but I will say I tried my best to be unbiased in this exercise, and I just pulled in a really good piece of equipment from a US manufacturer and a really good piece of equipment from an Asian manufacturer. With the NEEP database, I can look closely at its equipment. So say with the Carrier system, I see 36 in the model number. So 36 and 36 means 36,000 BTUs per hour, and there's 12,000 BTUs per ton. So I'm looking at a 3-ton system. When I'm in the NEEP database, I'll see this 3-ton system can actually remove 3.5 tons worth of heat from the home when it's 95 degrees outside. I'll see that the 3-ton system, when it's 47 degrees outside, can actually add 43,000 BTUs worth of heat. But by the time it's 5 degrees outside, it can only add less than 2 tons worth of heat. So the NEEP database is really great because you can look and see how the different equipment performs across the temperature spectrum. Say with the Mitsubishi equipment, a 3-ton system, its max that it can do in cooling is actually 3 tons. If I look at what it can do in heating, whether it's 47 degrees outside or 5 degrees outside, it can add in over 3 tons worth of heat. So as the temperature drops, its total heating capacity doesn't fall below its nominal capacity. Okay, so that's what it's rated at. So let's go and just highlight this. So here's some things to note about like how reputable US manufacturer, reputable HVAC contractors would feel about the US equipment. So with your traditional thermostat, you can have it to heat, you can have it to cool, and then you just set a temperature. And then the entire house is going to be at that temperature. Say on your car, if you just look at your climate control system, you can be doing a lot of different things with it. So in this example, you could be, say, heating the back of the car differently than heating the front of the car. You could be cooling the back of the car while heating the front of the car. You could be using your car's HVAC system to be defrosting your window. You could be using your car's HVAC system to be wicking away any moisture that's condensing on the inside of your windshield. You could be running the system in heat to be warming up your windshield while also running the AC to be wicking away the moisture. So it's not that like we're unaccustomed to doing like cool things or accomplishing things with our climate control systems with our cars. Like we should potentially be doing all of that with our homes as well. So with the US equipment, there's a lot of different ways that you could be doing that. So you can be doing it with, say, a rich ecosystem of smart thermostats and Wi-Fi thermostats and thermostats that have geofencing to know which occupants of the home are where. You could have cool air handlers that could be compatible with hydronics. You can have different evaporator coils so that it's communicating with the latest heat pump without changing up the existing blower motor or fan coil. You can have really robust air purifiers. You can have UV lights incorporated with it. You can have humidifiers adding moisture into the airstream. You can have ventilators that are going to be exhausting stale air and bringing in fresh air. Like all of this stuff is very much a reality and somewhat easy to the controls of it are somewhat easy for contractors to understand. So this is like the benefits of like the US equipment. Like this is where I see it, is that like it's really easy to put in a modern dual fuel system to be improving indoor air quality, providing affordable heat, but you're going to be always tied to fossil fuels. One thing to know with another difference between the two is that most of the equipment from US manufacturers are running somewhere between like 65 to just shy of 90 decibels. So the equipment itself is kind of loud compared to the Asian equipment, where most of the outdoor equipment is peaking around 55 decibels. So if we are just kind of looking at this chart, that's somewhere between chat and rain as far as the total sound level. However, a lot of the US equipment sounds more like an automobile. And every time that you go up 10 decibels, the sound pressure is actually doubling. So it seems like, oh, is there really that much of a difference between 55 and 75? And the answer is yes, it sounds like 2 to 3 times louder. So do know that the noise considerations are real. And with the central heat pumps from US manufacturers, when you're thinking about what times it's going to be running at its loudest setting, it's like overnight in the winter time. So it's usually not running at its loudest setting during the day, it is overnight. So that's something to be conscientious of. So we looked briefly at the NEEP database before, and we've kind of seen a version of this chart, and I just put in a link into the chat so you guys can access this so you can start playing around with it yourself. But here's an example of a heat pump of how the different types of equipment would be performing. So let's just follow this blue line real quick. So say if it's 70 degrees outside and you want your house to be 70 degrees inside, you're going to need 0 units of heat or 0 BTUs per hour. And this particular home has a design temperature somewhere around 36,000 BTUs worth of heat. Okay, so say when it's 10-ish degrees outside, you're going to need a heating system to add 36-ish thousand BTUs worth of heat to replace the 36-ish thousand BTUs worth of heat that is leaving every hour. We have 3 different pieces of equipment that I want to talk about. So option number 1 is you could be putting in a 5-ton system from Bosch, so a US or a European manufacturer. That heat pump starts off with a lot of heating capacity, but as the temperature drops, we're seeing that the capacity of the heat pump also drops. But if we look, because we started off with a 5-ton heat pump, we ended up with it having more heating capacity or more heating horsepower than the home would need. So this equipment from a US or European manufacturer could be the sole source of heat for the home. You don't need electric resistance, you don't need fossil fuels. Say if we put in a 3-ton system from Carrier or a 3-ton system from Bosch, it would have started off with more heating capacity or heating horsepower than the home would have needed. But because it did have a capacity drop somewhere around 25 degrees, that heat pump could no longer keep up. So the heat pump would need to turn off, fossil fuel-based system would turn on. Alternatively, we could have put in a 3-ton system from Mitsubishi or from Fujitsu or LG or Gree, and that is always going to have more heating capacity than the home would need. We're not going to talk about polar vortexes right now. We're just going to focus in on that design temperature and what each of those heat pumps does. So I want to highlight this as why that Bosch system is not a great setup. So with a heat pump, there are a heating system and there are a cooling system. So say if I put in that 5-ton Bosch system, I would see its minimum cooling capacity is 26,000 BTUs. It's over 2 tons. Say if I looked at the Carrier system that was right-sized for dual fuel, its minimum cooling capacity is 15,000 BTUs. And if I look at the Mitsubishi system, it's just shy of 10,000 BTUs. This is all important because say if the heating load is 3 tons, the cooling load is probably somewhere between 12 to 18,000 BTUs. Like that's as much cooling the home would ever need to get from 95 degrees down to 75 degrees. So with the Bosch system, the cooling is going to be wildly oversized. And what that ends up happening is the room, when you have, say, you have a, let's say 1-ton cooling load and a 2-ton cooling system, the room quickly gets to temperature, but the humidity inside of that room hasn't yet had the chance to be removed. And what this will feel like for the homeowner is it'll feel cold and clammy on most summer days where there's just a mild or moderate cooling load. with the right size equipment, it's going to be much more in line with having every chance in the world of removing both the heat as well as the humidity inside of the room or inside of this zone. So do know that like one of the purposes of an accurate manual J heat load calculation is not only to hone in the heating sizing, but when you are honing in the heating sizing, you're likely going to be making that heat pump system a much more comfortable central AC. The short cycling of load also reduces the equipment useful life. Yes. So Nicole wrote the short cycling of oversized equipment also reduces its useful life. And I think I included this. Did I include? Oh, no. I'll send you over some highlights from Mitsubishi. From Mitsubishi that will tell you all, like right from a manufacturer, they'll say all of the problems with oversizing equipment. But yeah, it also higher operating costs is very much real too. So it really is like comfort, cost, wear and tear, excess servicing. Like there's very little benefits of oversizing heat pump equipment, except for say polar vortexes. But for polar vortexes, I'll assure you there's a lot of additional ways to add heat into a home that is not going to impact the performance of your heating and cooling system for the remaining 99.5% of the year or 99.9% of the year. So just some of those. So some strategies for heat pumps that do have a capacity drop is electric resistance is what a lot of contractors do. It's not a good thing to see if someone does live in a town with investor-owned utilities. Fossil fuels can be used for a backup, and with the NEEP database, they have this advanced sizing feature where you can put in like what is the heat load of the home, what's the model number of the heat pump that you're looking at, and it will just tell you what percentage of the load is going to be served by the heat pump versus the backup. And sometimes the numbers aren't that bad. And sometimes with some manufacturers with how they wire the heat pump and the controls is that the heat pump will still be running. Like say the Carrier unit over here, the heat pump is still going to be running down, when it's 5 degrees outside, and it's just making up the difference with electric resistance. There's other types of heat pumps where once you reach the crossover point, the installers may say heat pump turn off, electric resistance turn on, and then the entire delta, the entire BTU amount that you're needing to be picking up is being picked up with just electric resistance, and that's very expensive. So, okay, so for integrated controls, I want to pivot back over and just talk about what these are and what these look like. So integrated controls are required in Mass Save land when you are putting in a dual fuel heat pump. Okay, so when you have an existing fossil fuel based system, you're not moving 100% to heat pumps, Mass Save is looking for integrated controls. The reasons why they want integrated controls to be put in are there's a few reasons to it. So number one, it's so that the utilities can claim the savings for the heat pump. And that's one of the primary reasons. Why users should be excited about integrated controls is it does allow for a much more seamless experience with having the heat pump system as your primary and the traditional fossil fuel-based system as your backup. So what this combination of integrated controls could look like is there's a Wi-Fi thermostat on your wall that's connected to your fossil fuel-based system. When the outdoor temperature falls below, say, 30 degrees, what will happen is this thermostat on your wall will communicate either with a third-party device or potentially directly to a ductless unit that has Wi-Fi built in, and will say, heat pump turn off, fossil fuel-based system turn on. When the outdoor temperature, say, climbs back over 30 degrees, it will say fossil fuel-based system turn on, turn off, heat pump turn on. So it just makes it guaranteed that the heat pumps are the primary heating system above 30 degrees, fossil fuel-based system below 30 degrees, unless you're on propane, and then Mass Save switches it over to 15 degrees. Some things that are nice about it in terms of like end user experience is like, one, heat pumps work best when you're setting them and forgetting them. So instead of having like the homeowner going and like turning off the unit, turning on the unit, and like the heat pump having a chance of running at its kind of like max capacity, it does kind of promote longer runtime with the heat pump of running at its min capacity, where it's running much more efficiently. I do feel like I should just go and let me just stop the share and change this over to the browser for a second. USA. Let's go over here and we'll just go to ductless unit. But additionally, some other kind of controls would be for integrated controls is you could have, say, a thermostat from Mitsubishi, and this thermostat from Mitsubishi is a wireless thermostat that is communicating directly to the ductless unit, because inside of the ductless unit, there is a wireless module built into it or purchased as an accessory. So sometimes the integrated controls for the ductless unit are built right into the system. What I was highlighting, Flare Pro, what I was showing off on that last slide over there is this, which is called like a Flare Puck Pro. And this is what most Mass Save and what a lot of Mass Save installers, what a lot of HVAC contractors in Massachusetts are doing, where that thermostat, instead of connecting directly to that unit, it's communicating to this contraption, which is just like, it looks like a little wall-mounted thermostat. But then this unit really serves the exact same way as the remote, with having like an infrared blaster. So this thing would just be blasting off and shooting off a infrared signal to tell that unit to go up in temperature, to tell that unit to go down in temperature, to turn on the unit, to turn off the unit. And one thing that's nice about the Flare Pucks is that each room now has kind of a visible temperature sensor. So you can kind of like hone in the overall comfort of the home that way. So do know that those are kind of two examples of integrated controls. And the last example of integrated controls would be, how did I shrink that down? The last example of integrated controls would be, let's just look back at this photo. You could just have the same Honeywell thermostat that we just saw on the previous slide. We could just have that communicating directly over to the zone controls over here, and that thermostat would just have would be having a primary and secondary terminals, and the primary would be the heat pump that's sitting directly on top of the furnace, and then the secondary would be the gas furnace. So the changeover can happen instantaneously. Sorry, there's one question in chat. Oh. I have one of these hybrid propane heat pump systems and mine has an outdoor sensor. Yeah, so with the outdoor sensor, so with Mass Save, do you know that for the outdoor sensor, it could be an outdoor sensor that is physically wired to the heating system, but with Wi-Fi thermostats, it is some of the models are pulling in real-time weather data. So sometimes the outdoor sensor is through data, and other times the outdoor sensor is something that is physically wired over to the outside from the heating system. And there are definitely best practices with with hardwired outdoor sensors, because say like sun and wind and shade and rain and ice and all of those things are real, and it could be potentially tripping up the unit. Okay. Let's get back over here. And sorry, screen share. Let's flip back over. Okay. So in some ways, this slide is just a tiny bit redundant, but I wanted just to highlight one thought is with Mass Save, the switchover point for propane is 15 degrees. So what Mass Save is saying is that all heat pump system that's tied to propane, the heat pump needs to be the sole source of heat from 15 degrees all the way up to 70 degrees. And that propane can only be the primary source of heat when it's below 15 degrees. Why I wanted to just spend a moment highlighting that is if I go to ASHRAE's design temperature data for like all of Massachusetts, is 15 degrees is unbelievably close to the vast majority of the state's design temperature. And to get the whole home heat pump rebate, you need to design a heat pump system between 90 and 120% of the building's heat load. So I do have a general argument that nobody should ever be pursuing the dual fuel rebate for propane, just because it's like if you are actually configuring the system as Mass Save wants it to be, kind of by default, you pretty much have enough heat pump capacity or heating capacity to be heating the whole home. And then with the price disparity with just how expensive propane is in Massachusetts, it like really doesn't make like any sense to ever be pursuing the dual fuel rebate for propane. If someone has propane, I would strongly suggest that they're just exploring like whole home cold climate heat pump systems without a capacity drop, because you're probably just only needing like 3,000 or 5,000 more BTUs per hour for like a whole home heat pump system, compared to like the dual fuel one with Mass Save as the partial home. All right, so one additional questions. Don't the US manufacturers make mini splits? So Joe asked, don't the US manufacturers make mini splits? And the answer is yes-ish. So they're one, they're all coming from Asia, and two, most of them are kind of white labeling an existing product from an Asian manufacturer. So say Trane is partnered with Mitsubishi, same thing with American Standard. So you buy an American Standard mini split, it's actually a Mitsubishi unit. With Carrier, they're partnered with Fujitsu, with like each one has its own Asian counterpart that they're partnering with and kind of white labeling their products. But with the IRA bill, there's a ton of money that's going to US manufacturers to be creating cold climate air source heat pumps. So hopefully we'll start seeing more of this equipment coming from US manufacturers, the same way that there's kind of like things in the bill that get a lot of people grumpy about EVs and also excited about EVs, but like all of the European car manufacturers are really grumpy that there's all these requirements for US manufacturing. It's kind of same things happening with heat pumps, where they are trying to be moving that market share over to the US. But as of the moment, I do think that most people are likely going to be better off today with buying the Asian equipment, or having it white labeled through a US manufacturer.